This video is going to be a long one, but by the end of it, you'll be able to understand the summary slide. In the summary slide, what I'm going to tell you is that if you want to find a transformation matrix given only the basis of the domain and codomain, as well as the formula, you'll be able to do that. Or if you want to describe a linear transformation in terms of a function, matrix, or just list it, you can also do that. So this will be the path that we're going to follow. I'm going to go through some refreshers, some basics that you need to know to understand the rest of the video, what a linear transformation is, some examples, how to do a linear transformation with respect to specific domains and codomains, then 5 examples so it stays in your brain, and then a summary. So, given two sets A and B, a function f, which maps A onto B, is a rule that assigns to each element of A a unique element of B, and this is how we often express it. Fa is the element of B assigned to A and is called the image of A under F. The set A is called the domain of F and is sometimes denoted dom F. The set B is called the codomain of F. The range of F, sometimes denoted range F, is a set of all elements of B that are the image of some element of A. So often Fa is defined by a rule, such as a plus 1 or a squared or a cubed, whatever you want. Sometimes Fa is defined by listing Fa for each A that is an element of A. So for example, this could be your domain 259, and then you can write F by doing this. It's a list, it's still a function. So if Fx is defined by some rule, and the domain of F is not explicitly stated, then we assume that the domain of F is a set of all values on which Fx is defined. So note that the range of F doesn't have to be the entire codomain. For instance, if we have a function that maps something in the vector space of all real numbers onto all real numbers, so dimension of 1, and the function is defined by fx equals ln x, then the codomain of F is all real numbers, but the range of the set will just be all positive, non-zero numbers. So now we can have a look at what a linear transformation is. So a linear transformation is a function from one vector space to another vector space, preserving the structure of the vector space. And in order to preserve the structure of a vector space, it must hold that it is, there are 2 rules that you need to fulfill. I did do a video on it, where it needs to be preserved under vector addition and scalar multiplication. We can also describe a linear transformation a number of ways. One way is through a function, another through a matrix, or through vector addition of the transform vectors, if the transform vectors were of the standard basis of our domain. So in other words, if we know the images under a linear transformation of each of the vectors in a basis, then the rest of the linear transform is completely determined. So let's do a couple of examples. So let our function map something from the second dimension vector space onto the third dimension vector space. And this is our linear transformation, which maps E1 to 112 and E2 to 0, 1, 1. So what is the formula of F2? Now remember that E1, E2 are just the standard bases. So in this case, because it is R2, this would be 0, this would be 1, 0, and this would be 0, 1. So let's find the formula. All linear transforms are linear, which means that we can find F2 by vector addition. So we know that f of xy is the same as f of x0 plus f of 0y. And we can take the x and y out to give us 1, 0 and 0, 1. And notice that if we put our 1, 0, which is a standard basis, E1 and E2, through the linear transformation, we will get 1, 1, 2 and 0, 1, 1. It's given in the question. So it's just x multiplied by the linear transform of our standard bases, and y as well. And then we multiply it back in, and that's it. We have our linear transform of f of xy. So see if you can do the next example by yourself. So let f be a linear transformation from R2 to R3, with our standard bases becoming 1, 2, 3 in the linear transformation, and 0, minus 1, 2 respectively. So determine f of xy. Pause the video, give it a go. So hopefully what you did is the first and the last example, where you separated f of x0 and f of 0y, and then you took the x and y out, and because we're given f of 1, 0, we can just substitute this into here to give us our linear transform of the standard bases. And then of course we add them, and that will be our function. This is our linear transformation. And that's great. If you got that, well done. So how do we do a linear transformation with respect to specific domains and codomains? Because we just did one with standard bases. So in other words, what do you do when you want to find the linear transformation of a function when you don't have a standard basis, but specifically define domains and codomains? So this is a formal definition. So transforming a vector in domain D to codomain C will give you the image of the vector. The image of the vector from D, or f of A, can be expressed in terms of the basis vectors of the codomain C. The coefficients of the linear combination you use to express the image of FA, or FA is the image, in terms of the basis vectors of your codomain will form the column vectors of your transformation matrix, i.e., the image of each basis vector can be expressed in terms of the basis vectors of the codomain, and the numbers you need to multiply to add the basis vectors to create the image of the vector is one of the columns of your transformation matrix. Don't worry, if you don't get it, we're about to do 5 examples. So the transformation matrix with the column vectors, which are images of the domain in terms of the basis vectors of the codomain C, is represented as such. So don't get, mostly in the examples I will use these ones and these ones. I won't use this one, but you can use that, it's technically correct. The main thing to note is that the codomain always goes first because your transformation matrix is in terms of the coordinates of the codomain basis vectors. So the transformation matrix with the column vectors, images of the domain in terms of the basis vectors of the codomain C, can be multiplied by any vector in the domain of D to give a vector in terms of the basis vectors of the codomain, which is essentially saying what this formula is. If you have any vector in your domain and you multiply it by the transformation matrix, you will just get that vector in terms of the basis vectors of the codomain C. Alright, let's do 5 examples so it stays in your brain. So example 1. Find the matrix of the reflection in R2 through the line x plus y equals 0 with respect to the standard basis S for domain and codomain. Right, so we have our standard bases E1 and E2, 1, 0 and 0, 1 because it wants set with respect to the standard basis S for the domain and codomain. So all we have to do is plug this through our function, which you can figure out here what y and x are respectively, and those will be your transformed bases, matrices through the linear transformation. And so all our transformation matrix is, in this case, is 0, minus 1 and minus 1, 0. And if we want to find what other vectors in our domain would become if we transformed it or put it through this linear transform, all we'd have to do is multiply it by this transformation matrix to get our vector. So we can either put the vector through this equation and figure it out manually, or just multiply it by a transformation matrix, which I think is much quicker. So here is our transformation matrix, which means that any vector that we put in, the coordinates will become negative of what they were initially. So example 2, find the transform matrix with respect to the domain B and codomain C. So in tests they will trip you up, it won't always be D and it won't always be C, they might do AB or DH or something. I've never seen DH, but you know, it can happen. So let a function map something from R2 to R2, and the transformation formula is given as such, and this is our domain and this is our codomain. So the first thing to do is find the image of our first basis vector in our domain, which would be 2, 0. So what is this in terms of the basis for the codomain, i.e. what is f of v1 in terms of C? So to find this, we just need to find out the linear combination of the basis vectors in C that will give our transformed basis vector, which would just be 0, 2. And we donate it with a subscript C to denote this, to show that this is what we found. So we do the same with the second vector. So now we need to find the image of 2, 1, which is 3, 1, and then now we need to express that in terms of the basis vectors of C. So if we multiply the first basis vector by 2 and then add just one of the second basis vector of the codomain, we'll get our 2, 1, C. So this is what the image is in terms of the codomain. So this is our transformation matrix. Now we just list these as the columns. So as you can see, the codomain goes first and then the domain B to represent it. So all that's happening is that we have a transformation matrix and we're multiplying it by some vector in B, and it will just give us that vector in terms of the codomain C. It does seem like a mouthful, but this is why we're doing 5 examples, so you sort of get an intuition of it. And yeah, do the practice examples just so you can sort of understand the rhythm of everything. Alright, example 3. Find the matrix of G with respect to the bases C and D, where this is our C and this is our D. And our G is mapped from R2 to R2 and is defined by this transformation formula. So as before, we just need to find the image of our first basis vector in our domain and then represent it in terms of the basis vectors of D, in terms of the coordinates. So it's just 3, 3. And then we repeat the same here. So we find the image of the second basis vector of our domain and then we represent it in terms of D in our coordinates, so a linear combination of the basis vectors in our codomain. So our transformation matrix is as such 3, 3 and 1, 2. And yep, same thing goes here. So now that we have our transformation matrix, if we multiply it by any vector we want in our domain, we will get something like this. So example number 4. So let this be a function where we're mapping something from R2 to R3, and the linear transformation maps our basis vector to 1, 1, 2 and E2 to 0, 1, 1. Find the matrix of F5 with respect to the standard bases of R2 and R3. Okay, now what do we do? So of course, find the image. Always find the image. And this is denoted with a subscript SS to denote that it's respect to the standard bases of both our domain and codomain, because the other examples we did, they weren't all standard bases, they were just bases of the codomain. If they're both standard bases, then you denote it with a subscript SS. So now we want to find our transformation matrix with respect to the basis B of R2 and the basis C of R3. Alright, now what do we do? So we need to find F5 first, because if we don't know F5, how are we going to find the image of B? So if you can remember before, we actually found it through this process. So now we know the transformation formula for fxy. So now we can compute the image of B. So this is what we get, f of 1, 1 and 1, we get those respectively. And now we need to express these coordinates with respect to C. You know what I mean. So we just express it in terms of a linear combination. Sometimes if it's a little complicated, don't be shy to make up a matrix and perform Gaussian elimination to figure out what the coefficients are. It's totally acceptable. And then you do the same for the second basis vector of our domain to get it in terms of C. So now we need to express, there we go. That's it. That is our transformation matrix in terms with respect to the basis of our domain and our codomain. So whatever we want to multiply our matrix by, a vector of our domain, it will give us that vector in terms of the basis vectors of our codomain. So this is all the working out. For example 5, feel free to copy it down. Actually, I encourage you to copy it down and try to explain it to your dog or your cat or your plant or something, or your mum if she's not afraid. Give it a go. So this is it, the summary. So if you want to find a transformation matrix given only the basis of the domain and codomain, as well as the formula, you can do that now. And if you want to describe a linear transformation in terms of a function, matrix, or list, you can. So well done, you made it to the end of the video. Please watch it as many times as you like and practice it as many times as you like.